Okay, let's get started. Are there any questions about the homework? Let's just think some gross questions about the homework or anything like that. So, yes. Okay, so what is the question? The question, say it again, I didn't hear. I mean, what's the best, worst, and average case time you're going to get on this backtracking thing? Well, okay, so best case time, you can hard code your answer for one particular graph. And the moment it sees that graph, say, woof, I got it, right? So the best case is not going to be interesting, right? The worst case, this is an NP-complete problem. The worst case is going to be exponential, okay? And so on that level, it's not clear how interesting it is, okay? There's differences between 2 to the n and 3 to the n that in practice are a big deal. But in general, the problem, when you're using backtracking programs are hard to analyze the complexity of, because you're going to be, in the worst case, searching everything, but you're going to be trying to prune in ways that you don't search everything. And since if you do it cleverly, you're going to get rid of stuff. How much stuff you get probably depends upon the graphs, probably depends upon a lot of things. So bottom line is your program had better be exponential in the worst case. Again, anybody who comes up and says, mine runs an n squared, yours is wrong. Okay? Any questions? Any other questions about the homework? Yeah. Okay, so let's start with the description of the homework, since I was going to wait a little bit, but fine. What is our problem? The input is a graph. The output is a permutation of the vertices, such that if you take a look at the span of each edge, the biggest span is minimized. Okay? So let's think about a graph that I happen to be in my head actually thinking about now for some reason, which was this one. Okay? Let's say that my graph here is 1, 2, 3, 4, 5. Does everybody get that? That is a tree that we could lay out here. What would be a terrible permutation for this? A terrible permutation would be one that went 3, 2, 1, 4, 5. And why is that a terrible one? Because there is an edge from 3 to 5 that spans 1, 2, 3, 4. That is the maximum. Does everybody see that? So that is bad. Can anybody give me a better permutation? A better arrangement of the vertices so that the maximum, yes? 1, 2, 3, 4, 5. Let's look at that one. How good or bad is that one? 1 goes to 2, 2 goes to 3, 4, 3 goes to 4, and 5, and 4 goes to 5. Does everybody agree? This one looks much better. The biggest edges of size spans 2, right? There's 1 intermediary vertice, where before there was 3. Is there any way to make it so that this can only span 1 intermediary? Maybe there's an even better drawing. Can anyone argue with me whether there's a better drawing or not? Okay, if you find a better drawing, then that's good, but yeah? You're saying the problem is, look at 3. 3 is going to have to be between, here's 3. If I want every edge to span 1, if I put 4 and 5 on this case, everything's good, except what's the problem? I got to find room for 2. Does everybody see that? So I am doomed to having at least 1 edge span 2. Okay? Here is a solution where at least 1 edge spans 2. Okay? So this is a optimal solution. Are there any other optimal solutions? Can someone else give me a good solution here? What happens if I reverse 2 and 1? Now what do I have? 2 goes to 1, and it also goes to 3. 1 goes to 3, and it also goes to 2. 3 goes to 4, and to 5, and 4 goes to 5. What is the length of the longest edge on this one? Yeah? Still 2. Does everybody see that? Is this one better or worse than the other one? You say worse. Well, by our criteria, which is we only care about the largest edge, the answer is they are the same. Does everybody see that? So this is equally good as this one by the standards of the contest, right? Any questions about that? So if you have ties, any one that is tied is good enough. Okay? Does everybody kind of get that idea? Okay, you don't have to output all of the ones that are tied. Why? What if I gave you a graph with no edges at all? What would be the best solution? If I had one that was just n disconnected vertices, what would be the best solution? Yeah? Any of them. So if I ask for all of them, you got to print out n factorial, right? And it would take forever. Okay? I'm asking you to give me one of the best ones. Okay? Any questions? This is a key to making it fast, is to not generate billions of copies of the same best one, of equally good solutions. Yes?
Is there a straightforward rule for determining what the minimum possible could be?
Is there a straightforward rule for determining what the minimum possible one is? The answer is no. Okay? If there was a straightforward rule for giving you the answer, then the problem wouldn't be a hard problem. Okay? Well, what you can do is you can come up with upper and lower bounds on it, and that's kind of an interesting point. Any solution you see is an upper bound on the best, right? It might, if I give you a solution where the biggest edge was 3, might there be, is the optimal solution going to be one where the biggest edge is going to be 4? No. So, you know, the solution is less than or equal to what your example is, right? And there may be observations that are helpful, that are going to say that the best possible solution has to be at least so big. How did we decide that this thing had to have a solution where it was always going to be a vertex skipped? That was based on the degree of a vertex, right? And so you want to, the game, the name of the game we're really playing is upper bounds and lower bounds. Okay? You want to stop when you can prove that there is no better solution. Okay? And you want to throw something away when it can't lead to a better solution than you have. Any questions? Okay, and we'll talk about pruning today, but that's the big picture gestalt of what we're trying to do here. Any questions? Okay, some people have asked me, can I do homework, use my late on homework 1? The answer is yes, you can. It's like any other homework. Negotiate with your partner so that nobody comes to blows about homework 5 if you do. But on the other hand, I don't guarantee I'm going to use the ones that came in late for the contest to decide who's the fastest, the champion. Any questions? Yes?
So homework 3 grading starts today?
Homework 3 grading will start when homework 3 grading should start, which I think is a week after it's turned in. Okay? But you guys will get the announcement. If there are, by the way, if there are homework questions about, you know, my, my grade wasn't right they didn't grade my homework right for some reason. The person to talk to is Santiago, the TA, not me. I forward all the requests there. But one thing I did have him compute, which I hope will make you people feel better, okay, is I did have compute what was the correlation between people's homework 1 scores and homework 2 scores. So if we assume that students were randomly assigning grades to the homeworks, then there should be no correlation, right? A good student on one homework it tells you nothing about their second homework, right? The correlation came out to be a 0.63, which means that there is a substantial correlation between how you did on one homework and another. Does that mean that everyone's graded perfectly? No. Does that mean that they're graded randomly? No, also. Okay? So we will continue to investigate and see how things happen. But meanwhile, do the best you can, learn what you can from the homeworks, and don't worry so much about it. Any questions? Yes?
The winner of the contest
The winner of the contest will win a prize, okay? I also threatened the person who's at the slowest program, I'm going to give them a prize. But we will see. I have a prize in mind, but I usually don't give it, I'll confess. Any questions, okay? To be honest, the prize I always think I'm going to give the slowest one was some X-lax, so their program would run faster. Okay, but anyway, any questions about that? Okay? Okay, yes, so there will be a prize to the fastest program. Okay, any questions about what the bandwidth problem is? Okay, let's go back now to how we're going to do this, because again, I want us to go through this thing. The key thing is you're going to be using backtracking. What was backtracking? It is a depth-first search-like thing where we're searching all possible configurations that are possible, and by building a solution vector one step at a time. And the key to making a depth-first search work is, for whatever problem you want, is writing the problems. Is your partial solution a solution? If it is, what do you want to do with it? And the key thing is, given that you have a partial configuration of things, and you're trying to fill the k plus first slot, given the input to your problem, and given what you've already put down in your solution vector, what are the possible candidates for the next position? Okay? And when you fill those out, that is what governs a backtracking solution. Any questions? I showed you how to do it for subsets last time. Let's do it for permutations, because permutations is the case that you're really going to care about, because this problem is a lot like a permutation. You know, the vanilla algorithm for this is construct all permutations of the vertices, see what the length of the longest implied edge is, and take the permutation that minimizes that. Okay? So what is the idea? We need to first think, what is our solution vector? And I would say that the obvious solution vector is going to be, we have an array of up to n elements, and we're going to put fill in the permutation one element at a time, right? So we're going to put in the first position, the second position, the third, whatever order, okay? But we're going to fill it in. And when we write the final permutation is just going to be the contents of the array. Any questions about my representation here? Okay. If so, what are my candidates? Because that's usually the most interesting one. What are my candidates for the next position in the array? Okay. How would I describe that? Okay. Anybody? Yes. Everything that's not in the array. Does everybody see it? If n is equal to 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, the original candidates were 1, 2, 3, 4, 5, 6, 7. I can't put a 1 down because the 1's already been used. I can't put a 3 down because the 3's been used. And I can't put a 4 down because the 4's been used. Does everybody see that? So my candidates are all the elements that were not already there. Does everybody see that? When do I have a complete solution? How do I test whether or not my solution vector gives me a complete solution? What would be that test about? Yeah? When k equals n, when I filled up all slots of my array with items that were not there before. Does everybody see that? And what do I do when I have a solution? Well, why did you want that permutation in the first place? Maybe you wanted to print it out to have a collection of permutations to hang on your wall. Maybe you wanted to now take that permutation and figure out what longest edge that implied, right? If you wanted to solve a backtracking thing. But process solution would be where you would do it, because now you got the permutation. Any questions about that? What does the implementation look like? For me and mine, I did the construct candidates the same way that he did. Basically, I set up a Boolean vector perm and said, is every item in the permutation? Originally, no. Then I went through all the elements of my partial solution and set the ith bit true if I is in the permutation. And then what did I do to construct my candidates? I went through my bit vector and said, if the item is not in the permutation, add it to the candidates and jack the number of candidates up by 1. Any questions about that? And what do I do for the rest of it? Is it a solution? It is if k equals n. And what do I do with it? Here I tried to say print it. Okay, but you can do whatever you want depending upon what your need is. Any questions about how you do, construct permutations? Okay. Good. So look at this carefully in the book and otherwise, because this is the basis of what you're going to be doing. Okay. You've also got to, how do you call it? You have to call it from an initial solution. So originally I'm trying to fill my array with all permutations of size n where I'm starting from the 0th position. Getting that index right, is it 0 or 1 to start, depends exactly on how you program it. Any questions? Okay, good. Now, okay, let me tell you a little bit more about the contest since I'm here, while I'm here. Again, just to remind you guys, you're going to want to do this separately. You're going to want to start on small files before you do big files, because your program will run out of gas on a file size. Okay? You will be graded on how fast it is, okay? But that doesn't stop you from actually adding comments and anything like that. Does everybody see that? Okay. And I'm going to want you to turn in your source code. I'm going to want you to turn in a printout, a file of the output of what your program's doing. And I want you to just write a little brief description about anything interesting you did to optimize this or something like that. And my goal is, what I'm really going to be most interested in is, what is the largest size file you can handle in 1 minute of sitting there waiting? Any questions? Yes? Does the power of the computer affect it? The answer is yes. Does it significantly affect it? The answer is no. Suppose your computer is 10 times faster than mine. Would that make a difference? Not really. This is a 2 to the n, you get an exponential time algorithm. Okay? It takes, let's say it's a 2 to the n algorithm. Algorithm takes 2 to the n time. How much bigger an n do you have to increase n to eat up, in terms of size, to eat up a factor of 10 in running time? Increase the number of vertices by 3 or 4. That is about what the difference of that extra number of, that extra 10 times faster computer is going to do, right? So if his program runs out of gas on something of size 50, and his computer is bicycle powered, okay, and you've got one that's 10 times faster, you could now, the same program will run up to size 58, okay? That's not a significant difference, right? This is why I am asking not how much time did it take to compute something, but where do you get tired of waiting, okay? And that's why I'm quite cavalier about what computer you use, okay? Any questions? This is why I don't care about what programming language you guys use. Some of you are going to say, ha, 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 I'm going to write this in assembly language. I'm going to really... And that's not a big deal. Why? Because the assembly language may be 10 times faster than what you would do. But I don't care about a factor of 10 here. I care about a big improvement, and that's going to come from pruning. Any question? Just so what I expect, many people's program will run out of gas around 10 or so. Some others will run out of gas around 15. The better programs will go substantially beyond that, okay? But they will run out of gas before my biggest example, okay? Any questions? Okay? So recognize that moving up in class to another 5 vertices bigger is an achievement, okay? Any questions? Okay, good. Okay, what are the rules for this thing to get your program doing it? Let me give you just some advice. First question is, don't optimize prematurely. Some people are busy saying, oh yeah, I can, you know, what you call, I can save, look at this, I can make this statement twice as fast by changing 2 times x to x plus x or something like that. Recognize these small level optimizations make your code look uglier. It's harder for you to continue to work with it, okay? So don't optimize prematurely, okay? Make sure you understand the ideas, make it clean. Worry about pruning criteria, because that is where the money is going to be. Any questions? Okay? Second, you're going to be using data structures, perhaps, at certain points to speed up computations. Make sure you use the right data structure, okay, for what you're actually doing, okay? So recognize what kind of operation you're doing again and again and again, and build your data structure to do that well. Should it be an adjacency list, or should it be an adjacency matrix? Should, you know, what do you need to store, okay? So you got to think about that. Any questions? The other thing that I will strongly suggest is there's this phrase, everybody knows what the word KISS means as an acronym for? K-I-S-S? Keep it simple, stupid, right? Has anyone ever heard that phrase? This is a good example of it. Some people are going, the winning program is going to be one of the shorter programs here. This is my prediction here, okay? Some people are going to be saying, if the graph is empty, I can make it run fast. I'll have a special program for dealing with empty graphs. I'll have stars, right? If a graph has a vertex that's connected to everything else, I can do that graph really fast. And they have lots of special cases in there. That is not the win, right? The win is on a simple thing that is going to have a general pruning that's going to try to prune as much of the space away as opposed to dealing with a lot of special cases, okay? And I recommend people start by doing something simple. First thing probably should be go through all the permutations and do the test. Then iterate on it to make it faster, okay? Any questions here? Okay? So the wrong thing is to say, go and saying, oh, I don't have any experience doing these kind of things, but I'm going to design the greatest possible pruning thing, and I'm going to take care of everything, and I'm going to implement this. Start simple and make it more complicated. Any questions? Okay? And the final bit of advice for programming is that you should know about that there is a thing called a profiler. I don't know, what language you use, I don't know. But there are tools that are designed to let you know where in your program is spending its running time. And in general, if you take a look at any computer program, okay, is this better? Okay, sorry about that. Okay, so anyway, there's a tool called a profiler, which has the property of telling you where your program is spending its time, what lines is it in. And almost any program has the property that there's a tiny number of lines where it is spending 90% of its time. And if so, you should know what those are. And maybe at the end, once you've done your tweaking of pruning and stuff like that, maybe that's where you want to now target for optimization. Any question? Yeah?
Will the computer we're using have multiple threads, or are we limited to one?
Okay, so some of you are saying, I can run it on multiple threads. How many threads are there on your computer? Does yours have, do you have 100 processors? Big deal. 100 processors. How much of a difference in size will 100 processors, keeping them maximally busy, do? Well, 2 to the, what is 100? 2 to the 6, 2 to the 7. First, you can't keep them all, what I will tell you is you won't be able to keep them all busy in more productive ways than by pruning. But even if you did, you only get a factor of 100 from it. We're looking for big wins, not something that's a factor of 100. Any questions? Okay. Okay, so let's talk about pruning now. Any questions? Actually, before that, let's do the problem of the day now to make sure we understand how to use backtracking to do something interesting. So a derangement is a permutation which has the property that no item is in its proper position. Okay? So what are the derangements on 4 vertices? Let's just think about what it means. A permutation where an item is no item is in its proper position. In the permutation 3, 1, 4, 2, 4, is there an item in the proper position? Yes. So this is not a derangement, right? Can anyone give me a derangement on 4 things? Yeah? 4, 3, 2, 1 is a derangement. Does everybody kind of see it? Can anyone give me another derangement? Yeah? 4, 3, 1, 2 is another derangement. Does everybody see that? Does anybody else have a favorite derangement? Yes? 3, 4, 1, 2 is another favorite derangement. Okay, fine. So there may be other ones. Does everybody kind of see it? What if I want to build a program to print out or count, if you wish, or do whatever you want with all derangements, okay, of n things? How could we do it? What is the thing that we need to do if we want to write a backtracking program? Let's think about it. What are the things we need to specify? Yes?
Well, if you want to generalize from the backtrack example you gave us, you could just change your is a solution to seeing that if any one index is the same as the original, then you just...
Okay, so again, what I want you to think, at least until you're, I think it's useful to think in terms of these 3 operations that you can change, right? And you're saying one way to do it is to change the, is a solution. Does everybody see that? He's going to say leave construct candidates the same, leave process solution the same. What is a solution going to look like now? Okay? It's going to look like if n equals k, right? That would mean that if n equals k, then we got a chance, right? And then what we're going to do is for I equals 1 to, n, okay, n, okay? And I'm going to say if a sub I is equal to I, then we say no, right? If n is less than k, or if k is less than n, we would say no. Otherwise, we would say yes. Does everybody see it? He's changing is a solution, right? Are there any other ways to do this? Yes?
When you're constructing candidates, then you do the check of where, after you filled in the solutions for what's already in the permutation, then whenever you're trying to find what's not in the permutation to add to the list, you say if I is equal, does not equal to k, then
Okay, so what she is saying is that before we agreed that the candidates for the ith position was going to be anything that was from 1 to n minus a1 to ai. Does everybody see it? We want to also rule out one other thing, right? What would be the other thing we would rule out? We're also going to say that you're also going to say minus I itself. Does everybody see it? If we never allow ourselves to put I into the proper position, we won't ever put it. Does everybody see that? So these are, I claim, the 2 classes of solution for this that make sense. One would be in the candidates for the ith position of the permutation, to eliminate I as a candidate and never construct anything that will ever be a derangement. The other is to basically, actually, the way I did this is a little bit wrong. I said put it in is a solution. I would probably say we could do the test for whether it's a derangement in process solution, right? We know that we want to stop our backtracking whenever we get a, well, the key thing is we don't want to fill past the array. Does everybody see that? Or I guess the number of candidates for the next position should be empty, so it should backtrack then. Bottom line is the two classes of solution we should agree are one where we explicitly forbid adding it, the other of which is we construct all permutations and select them out at the end. Okay? Which one is better? Let's take a vote. Okay? Who likes the solution of constructing all the permutations and pruning them out? Okay, well, a few people. Who likes the one of stopping it here? Okay, everybody likes that one. Why do you like that one? Yeah? Because you're saying it's a step we don't have to. You're saying it's simpler in code? Maybe, yeah?
So for the solution that I gave, an even better solution would be to not do the check for n equals k and check up to the current amount filled, so that if even a partial solution is already not a derangement.
You're saying check if a partial solution is not a derangement and then go back. But notice that that's sort of what she's doing here, right? Implicitly, the key thing is either we're going to stop and not generate it, or we're going to generate at the end and look at the end and decide what we want to keep and what we don't want to keep, right? Why do people like this solution better? Yeah? The potential advantage is that once that if we on the other end make the mistake of putting a 1 in that first spot, now we're going to generate all permutations, n minus 1 factorial permutations that can't be derangements. Does everybody see that? So it should smell that this one is much more efficient than the other one. How many people sense that? Okay? Your sense is what I consider to be good, but actually it's interesting that these two are both of the same efficiency. About. Why is that? Did anybody have a good enough combinatorics course where they counted the number of derangements of a of n items? Turns out the number of derangements of n items is n factorial over e. Okay? What is e? 2.718. Remember that thing? So what does this mean? If the number of derangements is n factorial over e, what does that mean? That means that 1 out of every third or fourth permutation is a derangement, right? Does everybody see it? If so, under that condition, is it much different to construct them all and throw out the ones that are not derangements, right? That'll be, I'm doing 3 times too much work, right? Versus pruning early, right? As it happens, because derangements are not a rare thing, I didn't gain that much by constructing, by stopping ever constructing them rather than pruning them. Okay? Do people get that intuition? Yeah. When you're in large data, would it affect it? The only thing that large data will affect is how happy you are to see n factorial, to print out. If you want to print out all the derangements, get a derangement collection. You can't do this for more than like n equals 10 or 11 anyway, because there's too many of them. Does everybody see that? So what's the point I want to make here? First, does everybody see that there's the way of pruning it immediately, and there's the way of generating everything and testing at the end? Which is better? Almost certainly pruning immediately. But if there's a huge number of solutions, it doesn't make much difference. Does everybody see it? If a large fraction of the search space is going to be solutions, it's not hard, you might as well construct and test. But how many solutions how many solutions are you going to want to print out for your bandwidth problem? 1. How many candidate solutions are there? N factorial, right? There you've got a very small number of solutions that you're accepting, right? So the odds that you're going to stumble across them frequently is no, right? So this is the better way to think about it. Any questions about that? Any questions about how you construct the derangements? Okay, good. Okay, so what I'd like to talk about now for the rest of the class is the question of pruning. Okay? So what you should... Does anybody want me to go through the iterations of the permutation generation algorithm to generate all 6 permutations of 3 things? Who wants me to do it? Who doesn't want me to do it? Okay, more people are emphatic about me not doing it. So, okay, good. Okay, what I'd like to talk about now is pruning. So generating all permutations meant going through and constructing everything. In generating the derangements, by cutting down an element, how did I prune the search space? By never putting I in the ith spot. Okay? I never would construct these n-1 factorial permutations starting with 1. Does everybody see that? Okay? So let's look at a related problem that some of you have seen. How many of you have ever seen the 8 queens problem? A bunch of you. This is a classic sort of example in dynamic programming. I mean, in backtracking. Where the goal is to take, in chess, a queen has the property that it can move up and down any row or column, and it can also move along anywhere along its diagonal. And what the 8 queens problem says is, given an 8x8 chessboard, can we find a way where we could put 8 queens down such that every queen is going to be safe from attack from every other queen? These queens are a bunch of rough customers. You don't want to get any queen threatened by any other queen. Any questions about that? If we have a 3x3 chessboard, is there any way to put down 3 queens on a 3x3 chessboard? Okay, is there any way to put down 3 queens on a 3x3 chessboard? Answer is no. I can either put it here, and if so, where on the second? I can't put a queen here, 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 here. I can put one there, but now I'm stuck. I can't put a queen here, and I can't put a queen here, right?
In order to discard a bunch of candidates, can we say that you have to have 1 queen?
First, we're not discarding candidates. Let's first go through this yet, and we'll develop that later. Okay? What about a 4x4 chessboard? Is there any way to put down 4x4 queens? Put queens on a 4x4 chessboard so that they threaten each other, that none of them threaten each other? Can anybody have a solution here? Yeah? So everybody see that in this case, the queens, the queens are all safe from each other, right? So in general, the problem is, how do we put these things down? Okay, any questions? And we want to use backtracking to try to help us do it. Okay, any questions? So the first question in using backtracking to solve a problem like that is, what is the solution vector going to be? Does everybody see this? I want to now describe my solution vector is going to be, basically describe where I'm putting the queens down. What should my solution vector look like? Okay, in terms of how long it is and what things I'm putting down there. Okay, anybody? Yeah. Okay, so one possibility, what you're saying is, you're describing a vector of length 8, okay? And for each one, you're going to describe the coordinate of the queen. You're going to say, where is my first queen, second queen, third queen, fourth queen, fifth queen, sixth queen? Does everybody see that? How would I describe the coordinates of the first queen? One way to do it would be to give you the coordinates x1, y1. Does everybody see that? Or if I've got an n by n chessboard, if I label the squares, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Does everybody agree that it's a number between 1 and n squared? Does everybody agree? So this would be basically 64 possibilities. Okay? And so in his arrangement, we've got a vector of length 8 where each thing has 64 possibilities. Any questions? Yes?
So in this puzzle, it becomes sort of quickly apparent that there has to be exactly one queen per row or column. So your vector could represent your row and the index could just be 1 through 8 in there.
Okay, now he's making an observation here, which is, actually, do I have this? No, this is too heavy, but it's, okay. He has made this observation that every row has at most one queen in it. Does everybody see that? Or equivalently, every column has at most one queen in it. Why does every column have at most one queen in it? Because if there were two queens in the same column, they would attack each other. Does everybody see that? So what does that mean? What is your representation of the space going to be?
So I've got an array of length 8, each one of which has one of 8 possibilities.
Does everybody see that his solution is he is going to have an array of length 8 where he's going to be telling me what is the column of queen 1, column of queen 2, column of queen 3. Does everybody see that? There's got to be a queen in the first row. Why do we need a queen in every row? We've got to have 8 queens. We can't put 2 queens in the same row, right? So every queen has to have its own row. Does everybody see that? So he's going to just give me the row. The column for the row 1 queen. And here there's only 8 choices. Does everybody see that? Which is a better representation? This one suggests you're iterating through 8 squares, each of which are 64 possibilities. How many of those are there?
Many.
Not many, but how many are there?
64 to the 8.
Does everybody see that if I got 64 here and 64 there, this is something like 64 to the 8th? Does everybody see that? And what is this one over here? This is going to be 8 to the 8th. How much potentially better is this solution than that solution? 8 to the 8th. What is 8 to the 8th? That's about 40,000 or so, right? So just picking this representation over that representation has a potential savings of about 40,000. See why I'm not caring about you and your 100-core machine? Okay? Because picking the right solution space makes a bigger difference than this. Okay? Any questions about that? Okay? Can anybody? Yes, question.
Since they're mirror images of each other, can we only use half?
Now you're saying, can we do even better? Okay? Do we really need to construct all 8 to the 8 possible things? Okay? Wouldn't it be good to note that, wait, they're saying that there's kind of a mirror symmetry here, right? How might we take advantage of that? Okay, it'd be nice if we didn't actually explicitly construct every solution and its reflection. That sounds wasteful, right? Let's hold that idea for a second. I have one thing I want to talk about first. Is there any other representation of this board that we might be able to use? There's a clumsier one that sometimes people see. They don't have a nice clumsy way to represent the board. Okay, now, okay, wait. Anyone have a clumsy way to represent the board? I'd like to see some stuff from the rest of the room. Yeah?
You have 64, and you say whether it has a queen or not.
Does everybody see that another way to do it would be to have a vector of size 64? Does everybody see it? 64, one for every square on the board. And here I'm allowed, true or false, is the thing have a queen in it? Does everybody get that idea? This is going to be what? This is 2 to the 64 possibilities. Does everybody kind of get that idea? And is this much bigger than even 8 to the 64 to the 8? What is 64 to the 8 in 2 to the something? Does everybody see that? Well, 64 would be what? 2 to the 6th. What's 2 to the 6th raised to the 8th power? Okay, that's 2 to the 48, I think. Okay, am I right about that? I always get this confused, right? Yes, this is 2 to the 48, right? Does everybody see that? So this is my, and what's this one, just for comparison? This is 2 to the what? This would be 2 to the 24. Does everybody see that? Okay. So there's a bit, now you can see how these compare, and yes, this is much smaller than this, which is much smaller than this, which is much smaller than that. Okay, any questions? Okay, any questions? Yes, question.
Because it's 2 to 64 combination, if you have a 64-bit processor, will that go faster than the box time?
You're saying, are there some games you might be able to play with, I've got a word length of 64 and I can glump, glump, glump it in one thing. So the answer, I would say, is this gets back to the kind of idea of you're worrying about trying to speed up constant factors rather than thinking about the big O kind of pruning thing, right? The good thing is that if you could glump it in all 64 in one step, is that better than doing 64 little steps? Yes, by a factor of 64. But that's not something that I want to be thinking about now, right? I saved 40,000, a factor of 40,000 by just choosing my array thing to be longer, right? So sometimes you can take advantage of big word lengths, but this is a sort of esoteric thing to do, okay? The bread and butter thing is how do I represent my search space small, and how do I take advantage of it? Any questions? Okay, now let's get back to this pruning thing. We had this symmetry idea going around here for a little bit, right? Is there any way that we can improve this idea of symmetry? Yeah?
If we can prove that the symmetry is necessarily the case, we could just do the first 4, right?
Okay, what he's saying now is if I want to construct only non-symmetric things, if I restrict the first position to being 1 through 4, then I won't construct the same solution twice. Does everybody see that? Again, I garbled my Queen's thing a little bit. Does everybody see here was my 4x4 solution? What would I get if I reflected this thing down the center? Does everybody see that I get another solution, right? If I put a, I simply reflect everything. This is what they're talking about, right? This would be this solution, this solution, this solution, this solution. Does everybody see that? So if I want to see go through all of these, maybe if I just restrict the first position to being in half the space, and then whenever I see a solution, I double it. I threw out half my search. Does everybody see it? And if Queen's solutions are rare, then I will still find all distinct Queen solutions. But it would take me about half the time as before, right? Any questions? Okay, and this is the idea that I want you to be thinking about in pruning. How do I take advantage of not looking at the whole space? Any questions? Okay, yes?
Are all of the solutions symmetric?
Well, are all the solutions symmetric? Okay, you have to convince yourself, is it clear that if I give you a solution, okay, where there is a queen on the first half of the board, there has to be a equivalent solution where that queen is on the other half of the board with this reflection idea. This is kind of a proof, I think. Okay, I may be being a little bit tongue-tied saying it. But what I am showing you is that if you have a solution on the where the queen is on the right side, top queen's on the right side of the board, if we simply replace each queen's position by column 8 minus I, we will come up with an alternate solution where, now the top queen is on the front part. Does everybody see? On the left side, right? So this is an argument that any solution with the top queen on the right side, if I reflect it, there is going to be an equivalent solution where it's on the left side. Okay? I don't think I was persuasive saying that, but that should be, I think, clear. Any questions? Okay, any questions about that? Okay, let's make this more concrete in case people are wondering a little bit ahead of where I want to be. What am I trying to say? Again, if I want to do this, using the right solution, this idea that I'm only going, that for every, there's got to be a queen in every row, and then I just have to specify the column, saves a factor of 40,000. And how do I do it? What is the critical thing? How do I... But the other question is, when I'm putting this thing down, what is my backtracking construct candidates going to look like? Maybe this is what we need to discuss. We all like this one, where we're constructing a vector of 8 things, and each one is a column from 1 to 8. What are my candidates for this column? For the queen on the 4th row? Does everybody see that? I have an n by n chessboard. I have put my first 3 queens down here. What are my candidates for the 4th queen for the 4th one? Okay? Anybody? What are the candidates I would have for the 4th one? Somebody else. I want to see some other people alive. Okay, yes? Well, it is true that if I've put down a column, let's say I had it like this. I can't put a queen in this column. I can't put a queen in this column, and I can't put a queen in this column. You're 100% right. But is that the only situations that I can't put people down? Yeah?
Basically, a cell around each cell which is true to the left, to the back, and to the top, to the bottom.
I also have to worry about diagonals. Does everybody see that? This guy here can also attack this square and this square by the diagonals. Does everybody see it? What are my construct candidates do for that row? It should be any number from 1 to 8 that represents a square that is not threatened by a queen I have already put down. Does everybody kind of see it? I want this queen to be safe. It will be safe if no other queen can threaten it. And it could be threatened by going one in the same column, that's bad news, or one on the same diagonal, right? So construct candidates has to figure out what are the safe places to put a queen on that row. Does everybody get that? How many people get it? How many people don't get it? Okay, any questions? So what is my construct candidates? This is my construct candidates for doing it. What am I going to do? Let's just look, again, there's different ways that, you can program this thing. But I am now going to say, is the ith column a safe place to put my queen? I'll assume that it's true unless until otherwise proven that. What am I going to say? For each of the queen positions before, for each of the current queens put down, there's up to k of them that we had been putting down. If the jth queen is sitting in column I, then I is not going to be a legal move. And likewise, this is a little bit difficult to see. How do I test whether something is a diagonal threat? It depends on it being as many rows up as it is over. Does everybody kind of get the idea of how you'd measure a diagonal threat? If I can be attacked by a queen 3 rows up, if I am 3 squares to the left or right of it. Does everybody get that? And so this is the test that I'm doing, basically. Is k minus j equal to the same as I minus... This is basically the diagonal threat. We can work through exactly what the bookkeeping is, but I claim that it's basically if a queen, a certain number of rows up from me, is the same number of squares over from me, that is where the threat comes diagonally. Okay, and so you can check that out, but this is basically the diagonal threat. So if there is no row or column that is causing no diagonal or column threat, then it's a legal move. If I've bombed out of this and it's still a legal move, then I'm going to add it to my candidates. Any questions about that? Okay? And this is the idea of how you speed up the search, because we are making sure we're only trying the possible candidates that can possibly help us. Any questions? And again, here we, in this case, all I did was count my number of solutions. Is it a solution? Well, it's a solution when I have filled up the board with queens. So it's k equal to n. Yeah? Does this consider this considers columns and diagonals? Why am I not worried about rows? It's having two queens in the same row. Yeah? Because basically each one of these things is, I'm only allowing myself to put one queen per row. Does everybody see it? My solution vector says what column is the queen in row 1, row 2, row 3, row 4. I'm never putting down two queens in the same row, because I'm only finding what is the one position of a queen in that row. Any questions? Okay, yes.
Can you, instead of having that, have a matrix, and that matrix would be exactly the same as a grid, and have a matrix, something that's diagonal, which cannot be there?
So, I mean, could I have made my solution vector, instead of a vector, make it a two-dimensional array, and explicitly put queens down in it? That is exactly my true false representation, isn't it? The vector of length 64 is kind of the same thing as a board of 8 by 8, right? And, so recognize that the logical question of whether one queen threatens another square or not, that is a bit of logic you have to implement. There's different ways to implement it. The way I did it was like this. You could put the queens down on a n by n board and decide if that helps you make that decision. But bottom line is I found I didn't need that. Okay? Any questions? Any other questions about this implementation? Okay? How would we have done this symmetry thing? Let's take a look at this. Suppose I wanted to count the number of n-queen solutions, and I wanted to make sure that I got all the solutions. Okay, we'll assume n is even. Let's say n is even, so I don't have to worry about what happens if it's on the middle boundary exactly. How would I add that to my program? What would I have to do to make this more efficient? Possibly cut the time complexity in half by exploiting the symmetry. What would I do? Yes?
I think you could solve either the upper triangle or the lower, then flip it and reflect it against the...
You say solve upper triangle or lower triangle. Let's think about the symmetry in the board, not triangular symmetry, although that's something else I could exploit, right? Let's just do the reflective symmetry here, right?
So there are 4 quadrants, right, in the board, like 4
Yeah.
4 by 4 squares, and if we can figure out a placement for one of them, we know that the one, diagonally opposite should, with the reflection, yield a fair combination. So if we can get, and also if we reflect it vertically, we get another one. So
Okay, so the way this, if we just wanted to eliminate the horizontal, the reflections around the middle, how would I do that? In my construct candidates, I would have a test up here. If k equals 1, then I would say the candidates are 1 through n over 2. Does everybody get that? Because I'm only going to allow myself to put it on the left side, the first queen on the left side. Then, when I got to the point where I wanted to count my number of solutions, here I'm counting it by 1 whenever I get a solution. knowing that there is an alternate solution where the queen, this first queen is going to be on the right side corresponding to it, how would I change my code? Well, multiply my addition of 1 by 2, which means basically count it up by 2. Does everybody see that? If all I want to do is to count the number of solutions, if I want to make it run, the program run twice as fast, all I had to do was say solution count plus plus, plus plus, meaning add by 2, or I say the solution count plus 2, and add a test up here. If k equals 1, my candidates are all on the left side of it. How many people believe that that'll work right? How many people are a little confused by that still? How many people are a lot confused by it? No one's raising their hands. So any questions? Okay? So this is the kind of thing that I want you guys to do. This is why I'm not worrying so much about you using 100 cores or anything like that. I want you to think about things like, how do you remove symmetries? How do you know when to give up? Okay? Any questions here? Okay? Any questions about the 8-queen solution? Because that's somewhat inspiring. Okay, good. Let me show you one other chess-related problem that is a personal favorite of mine. Because we were the first people to ever do this, so this is a personal favorite of mine. But there is a problem in chess, a kind of chess puzzle, which asks yourself whether there are any, there's 8 main pieces in chess. There's the queen, which can move in any row and column. There's the king that can move 1 square in any row or in any direction. There's the knight that can go ka-chunk, ka-chunk. The bishop can go along diagonals. The rooks go along columns and rows. In this configuration of chess pieces, 63 out of 64 squares on the board are being threatened by some piece. If I put each here, which piece is threatening this one? The 2 rooks are threatening. If I look over here, what's threatening this one? The queen. If I look over here, what's threatening this one? The knight. Does everybody see that? Which square on this board is not threatened? See if anybody can figure it out. Okay, is there any square on that board that is not threatened by anybody? Okay, let's look at this. Okay. Corners. Okay, I'm waiting for somebody to make me a serious proposal. Yes? This one you say no one's threatening? I think someone's got it. Who's got it? The bishop. Bunk, 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 bunk. Got it. Okay. Any other yeah? The one above the top knight. The one above the top knight. The bishop's got that one. Okay, is there any square that's not threatened? Yeah? The knight itself is this is the only square on the board that's not threatened, the top knight. Okay? Because that bishop is saving the knight's life from the rook. Does everybody see that? Okay? So in this configuration, 63 out of 64 squares are covered. Okay? Is there a way to put these pieces down so that all pieces are threatened, all squares are threatened? Okay? Any questions? Okay? And in fact, this problem was originally posed in 1849, okay? And no one had ever found a configuration where this was true. But how would we go about trying to find a configuration or prove it didn't exist? What is the basic idea we would want to use? Okay? What? Backtracking. Does everybody kind of get the idea that this is the kind of thing that backtracking was invented for? Okay? Out of all possible configurations, can we find a configuration such that all squares are threatened? Okay? Any questions about it? So how might we go about doing that? Okay? Let's think about what are degrees of freedom. What should the solution vector be for this problem? Does everybody get what the problem is? Is there a way to take all 64 squares and threaten them simultaneously with these 8 pieces? Okay? What should the solution vector to this thing look like? Does anyone want to make a proposal? Anybody else? Yes. Well, okay. I'd like to see some more action around the room, but yes.
You have the 8 pieces in each of their positions.
So one possibility is to say that, well, we're now expert 8 queen solvers, right? Why don't we use the same kind of a thing where maybe we're going to use, well, let's think about it. Which one of these configurations can we use? Is it true, and still true, that every column is only going to, every row is only going to have 1 piece in it? So we can't do this one, can we? What would be another thing we could do? We could say that we have a solution of 8 possibilities, and we give what is the square for each one of the pieces, right? We might say king, knight 1, knight 2, bishop 1, bishop 2, rook 1, rook 2. Does everybody see that? Yes, and then the queen. Does everybody see that? And here we specify the solution for it. Okay, any questions? We could, I guess, could we also do something where we had a vector that was of length 64 and we said what piece was on it? Yeah? How many possibilities of that would there be? Okay? For each one of these, there would be what? We have a choice of a 1, 2, 3, 4, I guess there's something like 5 or 6 different kinds of pieces, right? And a blank. So this would be something like 5 to the 64th. So this would be bad news. Does everybody agree? Yeah. Are bishops different colors? Well, what we could do is solve it, I don't know, okay, but let's say maybe, let's not enforce that. If we want to enforce that, that would, we can decide if we want to enforce that or not, right? How would we enforce whether or not we want the bishops on different colors? Whose job would that be? Is a solution's job, construct candidate's job, or process solution? Yeah?
I think
Construct candidates. The kind of thing that would be saying, if I have already put down a bishop on white, if this is going to be a bishop, it better be on a black one. Does everybody agree? Okay. So we agree that we want to do a vector-like thing, where basically we're going to give the positions of each piece and go through the coordinates of it, right? And this isn't the nice, fast 8 queens thing anymore. Now we're going through and slugging it out through that 2 to the 6th to the 64th type of, that was a 2 to the 48th type thing, right? Any questions? So if we go ahead on the slides, let's just see where we are. If we count how many solutions there are, there were a lot of solutions possible, okay? Enough so that going through all of them explicitly, especially at the time we did this, was not possible, okay? Any questions? So we would want to be able to do backtracking and pruning where we, where we look to see if there is a, okay, wait, so let's go back again. Let's think what we want to do. We kind of agree that the solution is going to be an array of size 8, which is going to tell us the position of each piece. Does everybody agree? And we've got 64 choices for the king, and 64 choices for the knight, and 64... Is there any way that we agree that if we go through all configurations, and then test at the end, we will eventually get to a solution. But we would have to construct all 2 to the 64th, all 2 to the, I think, 48th different solutions. Okay? Is there any way we can stop after a partial solution, however, and avoid actually putting down all the queens? All the pieces. Is there any way I can start to have putting down some of the pieces and now decided well, let's just think about it maybe a little more generally. Suppose I have put down the king in one place, the knight in another place, and the knight in another place, and now I'm putting down the first bishop. What are the possible positions that bishop can go to? Do you see that's what construct candidate's job is? What are the possible candidates for this bishop? Okay. Yeah? Well, in this case, does it have to be on the diagonal of anything? No, my goal is to put pieces down so I threaten all 64 squares, right? You're saying that if I put down a bishop, it's got to be on the diagonal of a piece that's safe. I don't know that that's true. Okay? Is there any criteria that's obvious to let me prune that? Yeah?
So, like, you don't want the spaces that it threatens to overlap a lot. So, like, if you have a queen and you put the bishop on the same diagonal as the queen.
So you're telling me that it can't possibly be the case that if I have a queen here, I would have a bishop next to it, because that's sort of, the bishop doesn't use to all of its power. Is that really impossible? It seems to me like you probably don't want to do it. But are you going to tell me absolutely that if you're trying to solve a problem people have been waited with bated breath for 100 years, you're absolutely sure that there is no way that the winning solution has that property? Unless you can prove to me that the winning solution does not have a queen next to a bishop. Then you got to try it out. Does everybody kind of get that idea? Okay, yeah?
You could pre-calculate the maximum spaces each thing could possibly cover, and then use that to figure out how much overlap.
Okay, so this is what turns out to be the interesting idea. Let's just see if I can take it. First of all, there's a way to exploit symmetry, right? If I'm trying to eliminate all possible board configurations, I don't want to search everything. Does everybody agree that since I win the moment I find a solution that covers all the squares, if I can find a way to eliminate duplicates, like for example, ensure that that one of the bishops has to be in the lower half, because if not, I could reflect it over to the other side, right? Or insist that the queen be in the last quadrant, because if not, I could just rotate the board around. So part of it is eliminating symmetry, okay, and making sure that I only see every configuration once. But a better idea that's maybe more apropos to what you're doing is to instead say, what if I get into the situation where I have put down a bunch of pieces here? And so far, let's say my last piece is a king, but I've put down everything but a king, and I still have 10 uncovered squares. Does everybody kind of see that as I put in more and more pieces? Usually the number of unthreatened squares is going to go down, right? What if I get to the point where I've put down every piece but the king, and I still have 10 unthreatened squares? Is there any possibility I can complete this to be a solution? No. Why is that? Because the king can only attack 8 squares. Does everybody see that? Okay. I need this last piece to have the power that it can threaten at least as many squares are open, right? But if I know how many squares are still open and the power of the pieces I haven't positioned, does everybody see that I can prune the moment I get to that point? How many people see this idea? Okay. So basically, if I ever come to a point in my permutation where I have put down k pieces, the number of uncovered squares is greater than the maximum possible coverage from the remaining pieces. At that point, I can backtrack. Does everybody see that? Okay, so how many candidates are there then for the next spot? No candidate can help me. And I say, under this condition, no candidate can help. It'll just backtrack and move something else around. Any questions? how would I put down the order of my pieces to maximize the power of this idea? Okay? Should the last piece that I put down, do I want it to be the king or do I want it to be the queen? Let's just think about this. Does everybody see that if I do this kind of pruning, there's different orderings for how you can put down pieces, right? We could have done king, rook, queen, rook, rook, bishop, bishop, knight, knight, king, which is, I think, a measure of power, right? That these things have more moves than the other. Or I could have put them down in the reverse order. King, knight, knight, bishop, bishop, rook, rook, queen. Which one of these would have been a better idea to put them down on if I want to get pruning to happen? Yeah?
First one?
The first one. Why do we think the first one might be a good one? Okay? Yeah?
It'll shoot up your coverage quickly, so that you...
The first one, if I put the big pieces down, I'm going to cover a lot of squares quickly, right? That's helpful, but what's the bigger advantage of pruning? Pruning is trying to eliminate things that are not going to be a solution. What is good about this order is that I have the weakest pieces at the end, right? Meaning the potential for these guys to save me from a partial solution is as limited as possible. Does everybody see that? So having it being the way I win is by eliminating solutions that can't make it. Okay? And so having the weakest pieces last gives me the greatest possibility of pruning it, right? If my queen was last, then I needed that I'd have to fill up the whole board unless they were more than 27 holes at the last position. Does that seem right? So does everybody see why this is the right order to maximize pruning? Okay? And this is the kind of thing that I need you guys to be able to do, okay, in your thing. Your goal is to try to think, how do I order these search so that I can eliminate as much of the search space as possible? Okay? Any questions about that? Okay? And so you guys should start by thinking, hey, wait a second, what is the solution to my, the solution space for my bandwidth problem? Well, it's probably going to look like these other permutation things, which means I'm probably going to build up a partial solution. What order should I put these guys in? Okay? How can I prove to myself that putting down these vertices so far can't help me so I can prune it away? That is the kind of thing that you guys got to be thinking about. Any questions? Any other questions about this kind of a scheme? Okay? Backtracking and combinatorial search is a powerful thing because it gives you a way to find exact solutions to problems that you couldn't otherwise do. And it's a good test for your cleverness to see how the pruning works. Okay, good luck. Work on it, and I'll see you guys next time.